Okay, this is Chapter 7, Section 2. It's about multiplying radicals. So we're going to get to this question in just a second, but I'm going to tell you the general form of multiplying radicals is that if this number on the outside is the same, then you can combine these two under a single radical by multiplying what's inside of each of the individual ones. So this number on the outside is called the index. N is called the index. So if the index is the same, you can multiply the two numbers that are inside. So here we have a square root and a square root, so that's 2 and 2. So the index is the same there. So that means I can combine these two under a single square root and multiply the two individuals, 2 times 8. So this is the square root of 16. We know the square root of 16 is equal to 4. So the square root of 2 times the square root of 8 is equal to 4. Let's do one more example of that with a cube root. Here the index is the same again, so we can combine these two expressions under one radical and multiply what was inside the two individuals. So now we have the cube root of negative 5 times 25, which is negative 125, and the cube root of negative 125 is negative 5. So if we multiply and simplify here, we end up with negative 5. Okay, let's do this one now. Again, we can combine them. Oh, so I had a bit of a lag on my computer. Okay, let's do this one now. So again, we can combine them under one radical, and you have negative 2 times 8, which gives you the square root of negative 16. There is no square root of negative 16, not a real number anyway, and so that's as simplified as you can get. Or I guess you could write it with imaginary numbers if you chose. You could write it as 4i. Okay, so now let's simplify something that looks like this. We could write this the opposite as we did on the last thing, where we have two separate square roots, and things that are perfect squares can go in the first, and things that are not perfect squares can go in the second. So we can break up 72 into stuff that is a perfect square and things that are not. So 72 is the same thing as 36 times 2. So I'm going to put 36 over here and 2 over here. 36 is a perfect square, 2 is not. X cubed could be written as x squared times x. X squared is a perfect square, so I'm going to put that over here, but x is not. And now I can simplify this expression. The square root of 36 is 6, and the square root of x squared is x, times the square root of 2x. Now remember, anytime you take the square root of a number that was raised to an even power, you need the absolute value bars here. So this is 6 times the absolute value of x times the square root of 2x. That's the simplified version of 72 times x cubed, the square root of all that. Okay, let's do it one more time, except this time with perfect cubes. So what we're going to do is we're going to rewrite this as an expression of things that are perfect cubes and things that are not. So what we want is we want to break 80 down into something that is a perfect cube and something that isn't. Well, 8 times 10 is equal to 80. 8 is a perfect cube and 10 is not. And 10 doesn't have any factors that are perfect cubes either, so I can write 8 over here and 10 over here. And then n, I can write n, that's the same thing as n cubed times n squared. N cubed is a perfect cube and n squared is not, so I write n cubed here and n squared there. Let me get some extra space. The cube root of 8 is 2, the cube root of n is n, and then times the cube root of 10 times n squared. So this is the simplified version of the cube root of 80 times n to the 5th. I'm going to leave this one as an exercise, and I'm going to skip to combining and then simplifying. Okay, so there's two ways you can do this problem. I'll do it kind of the more methodical way first, and then I'll show you the shortcut. So you can take the cube root of 54 times 5 times x squared times x cubed is x to the 5th, x cubed times y to the 4th is y to the 7th. I'm not sure what 54 times 5 is off the top of my head. 270, I believe. So we have 270 x to the 5th, y to the 7th. And now we can rewrite this as two things that are the product of two cube roots, and we're going to put the things that are perfect cubed over here on the left and the things that are not perfect cubes on the right. So 270 can be written as 27 times 10, and 27 is a perfect cube. X to the 5th can be written as x cubed times x squared, and y to the 7th can be written as y, well, I could write it as y cubed times y to the 4th, but then there's still a y cubed over here. So if I wrote it like this, I'll go ahead and do that and simplify it. I still have a perfect cube in this term. So I'll simplify this, and then I'll show you that I can actually pull out another and that you'll get the same. The cube root of 27 is 3. The cube root of x cubed is x, and the cube root of y cubed is y, times the cube root of 10x squared y to the 4th. And if you made a mistake and didn't pull out the highest factor, like I could have taken y to the 6th and left y here, then I still have a perfect cube I can pull out. So I would need to write the cube root of y cubed. I need to do that step again, essentially. 10x squared y. I take y to the 4th and I take that cube root out. The cube root of y cubed is y, and y times y is y squared. So I can rewrite this as 3xy squared. And this is the simplified version. Okay, I could have gotten to this step by doing the second step up here a little bit smarter. So I'm going to go ahead and do that. Okay, so I've taken out the 27 and the 10. I've split up the x cubed and the x squared. Y to the 7th. The highest thing that I can break y to the 7th into is y to the 6th times y. The reason why it's y to the 6th is because 6 is a multiple of 3. So I wanted the highest multiple of 3 that was also a factor of y to the 7th. So I'll write y to the 6th here and y there. Now the cube root of 27 is 3, the cube root of x cubed is x, and the cube root of y to the 6th is y squared. And then I take the cube root of 10x squared y. And that's what it simplifies to. Now I told you there was another way to do this. You could have kind of just used these, since I'm going to do factors anyway, I can think of these as chunks. And I'm going to go ahead and just skip to putting the perfect cubes here and the things that are not perfect cubes over here. So 54, I could write that as, that's the same thing as 2 times 27. So let's write 2 times 27. X squared is not a perfect cube. Y cube is a perfect cube. So I'm going to put the 27 here, and I'll put the 2 over here. And I'm going to put the x squared over here also. So I'm kind of breaking up this first term, and then I'm going to put y cubed over here. So now I've broken up just this first expression right here, and I've put the 27 here and the y cubed here, and then I put 2x squared over there. Now I'm going to go to the second term. 5 is not a perfect cube, so I'm going to put it over here also. So times 5, and then x cubed is a perfect cube, and then y to the 4th has a perfect cube in it, and it has one that isn't, so I'll put that over there. So let's rewrite this in a way that looks a lot nicer. So I put 27, I have y cubed and y cubed, so that's y to the 6th, and then I have x cubed, and then over here I have 2 times 5, which is 10, x squared y, and then I can take the perfect cubes and rewrite the expression that was on the right. So whichever of those two methods you find easier, those are two ways to solve this problem. Okay, so there's a couple ways that you could do this. I'm going to do it kind of the more standard methodical way first again. The 2 is already on the outside, so I'm going to leave that out here. 7 times 21 gives you 147. And then x cubed times x cubed gives you x to the 6th, and then you have y squared. Okay, now let's break this up into things that are perfect squares and things that are not. 147 is the same thing as 49 times 3, and that's not at all obvious, but it is. And then x to the 6th and y squared are also perfect squares. So square root of 3, the 3 is the only thing that's not a perfect square in this whole thing. The square root of 49 is 7, so I have 2 times 7. The square root of x to the 6th is x cubed, but since x is raised to the 6th and you're taking the square root, you need the absolute value of x cubed. And y squared, the square root of that is y, but you also need that to be in the absolute value, because x cubed or y could be a negative number, but when you take x to the 6th y squared, that's going to make it a positive number, and then when you take the square root of that, it's always going to be a positive number. So those absolute value bars are necessary there, and then times the square root of 3. So this is 14 times the absolute value of x cubed y times the square root of 3. Okay, the other method that you could use to solve this is combining them under one square root, but don't multiply these two numbers together. So leave the 2 out here again and just do 7 times 21, x cubed times x cubed, and then times y squared. You can combine those if you want, because it's not really going to make much of a difference there. But if you notice that 21 is the same thing as 7 times 3, that's a lot easier than knowing 147 divided by 49 is 3. But you see 7 times 7 is 49 times 3. Anyway, this makes the next step a little bit easier. Take the square root of the perfect squares. You're going to have 7 squared. You're going to have x to the 6th and y squared, and then times the square root of 3. I'm going to rewrite this as 7x cubed y squared. The inside could be rewritten that way. And then the square root of a square is just the stuff that was inside, but you need to put the absolute value because we have the two even numbers here. Now 7 can't be a negative number, it's just 7, so you can bring that out and multiply and you'd have the same thing. 14 x cubed y times the square root of 3. Okay, another property, the square root of 36 is the same thing as 6. The square root of 25 is the same thing as 5. So this is equal to 6 over 5, but it's also equal to the square root of 36 over 25. You could rewrite it that way if you want. This isn't a great example of that, but this is the same thing as the square root of 6 over 5 squared. And those two things are going to cancel out and you'll be left with 6/5. Okay, so let's do that with an example that's slightly more interesting. You could combine these over one in one radical, similarly to the way that you can combine multiplication. And the reason why that's useful is now you can simplify. 32 over negative 4 is negative 8. So this is the same thing as the cube root of negative 8, which is negative 2. So combining and simplifying first when you're dealing with fractions and radicals is a really good strategy, especially when you're dealing with variables. So I'm going to rewrite this as the cube root of 162x to the 5th over 3x squared. And now I'm going to combine this in a simplified version if I can. That's the cube root. 162 divided by 3, you can actually simplify that. 3 goes into 16 5 times with a remainder of 1. And then it goes into 12 4 times. So that's 54. X to the 5th over x squared is the same thing as x cubed. Now we can rewrite this as some things that are perfect cubes and some things that aren't. 27 is a perfect cube and 2 is not. And then x cubed is a perfect cube. So we would have 3x times the cube root of 2. That's what this expression simplifies to. I'll do one more example of that. That's the fourth root of 1024x to the 15 over 4x. I combined it as under one radical. 1024 divided by 4 is 256. And then x to the 15 over x is just x to the 14. And we have the fourth root of this. The fourth root of 256 is going to be 4. And, well, let me rewrite the whole thing like this. You're going to have things that are perfect fourth roots and things that are not. X to the 12th. 12 is a multiple of 4, and so I can pull out 12 x's, and I have to leave 2 x's inside. The fourth root of 256 is 4. The fourth root of x to the 12th is x cubed, but again we need those absolute values because we had an even number and an even number there. So let me write that a little bit nicer. 4 times the absolute value of x cubed times the fourth root of x squared. Okay, now we're going to talk about rationalizing the denominator. So to rationalize the denominator, what that means is we don't want to have a radical on the denominator. This is an irrational number. The square root of 3 is. So we're going to multiply by something that gets rid of that irrational number. And we're going to multiply by the same thing, the square root of 3, because 3 squared, the square root of 3 squared, is going to give us a rational number. Square root of 2 times the square root of 3 is the same thing as square root of 2 times 3. Square root of 3 times the square root of 3 is the same thing as the square root of 3 times 3, which gives us the square root of 6 over the square root of 9. Square root of 6 we can't simplify, but the square root of 9 we know is 3. And now we have a rational number on the denominator, which is what we wanted to do, hence the name rationalizing the denominator. So let's do the same thing but with variables. We're going to multiply by something that will make the bottom rational. And in this case, we're going to multiply by the same thing that's on the bottom of the other side over here, because if we multiply by 5, it's going to make that 5 rational. We're going to get x squared, which will make that rational, and y squared, which makes that rational also. On the top, we have 5x to the 4th y, and on the bottom, we have 5 squared. We just have the entire thing squared. I'll write it like that. We have 5xy squared. These are going to cancel out, and we have the square root of 5x to the 4th y over 5xy. And we can simplify this top a bit. The square root of x to the 4th can be simplified over 5xy. The square root of x to the 4th is going to be the absolute value. Oh, actually we don't need the absolute value. Square root of x to the 4th is going to be x squared, which is always a positive number, so we don't need the absolute value. And we can actually cancel an x here, and we'll be left with x times the square root of 5y all over 5y. And that's the rationalized version of this. Okay, last example. So now we need to rewrite this. Since we can't simplify anything, we're going to rewrite it as 2 separate fractions, and we're going to rationalize the denominator. So we need to multiply by something. We have to multiply by a cube root because that's the only way we can combine these things. And we want to multiply by something that's going to turn this 3 into a rational number. Since we're taking a cube root, we want to multiply by 3 squared. And you'll see why I picked that number in a second, and x squared. And we're going to do the same thing here, 3 squared and x squared. So multiplying across on the top, I get 3 squared is 9, and 9 times 2 is 18, 18x squared. And then on the bottom, I get the cube root of 3. 3 times 3 squared is the same thing as 3 cubed, and x times x squared is the same thing as x cubed. So now you can see that the bottom is going to simplify. The top will stay the same, and the bottom simplifies to 3x. And now we have a rational number on the denominator. So I chose the numbers that I was going to multiply by on the top and bottom to be the same in a smart way so that it cancels out down here. Notice I'm always multiplying by the same thing on the top and the bottom. That's because I'm multiplying by 1. I'm multiplying this fraction by 1, a very strange looking 1, but in a smart way to rewrite this so that the denominator is rational. So if you have e equals mc squared, we're going to solve this for the variable c. So the first step would be to divide by m on both sides, and you would get e over m equals c squared. Well, then the next step is to take the square root of both sides, and you get the square root over e over m is equal to c squared. But now it wants us to rationalize the denominator. So I'm going to rewrite this as the square root of e over the square root of m is equal to c. Sorry, this was the square root of c squared. And so now I need to rationalize the denominator. I need to change this expression to something that's equivalent but doesn't have an irrational number in the denominator. So I'm going to multiply the square root of e over the square root of m times the square root of m over the square root of m. I'm just multiplying by 1, so it doesn't change the value of the left side of this equation at all, but it's going to rationalize the denominator. So I get the square root of e times m on the top, and on the bottom I get the square root of m squared, which is just equal to m. So c is equal to the square root of e times m over m.